So, as we did in week 1 when we were working with linear functions, we were interpreting things back then like the y-intercept, the x-intercept, and the slope in the context of a problem. We'd like to do that now that we know about derivatives. And this, again, is keeping with the whole thing about looking at derivatives in a variety of ways. Here you'll notice that we don't have any formulas for the actual functions. We just have some values of the functions, looking at them numerically, and we have a story to go with them, looking at them verbally. So here our function, capital L of capital T, gives the length in millimeters of a metal bar when it's heated to a temperature of T degrees Celsius. We'd like to interpret a couple different things and then use them to do something. So here there's no derivatives happening yet. All we have to be careful about is to get the units right. The only way to get this part wrong is to get the input and the output mixed up. So give yourself a second here, try to decide, is this the 500, is that the temperature, or is that the length? And I hope you decided that that was the temperature. So this says at a temperature of 500 degrees Celsius, what's happening, or maybe nothing's happening, but what is the state? This 30,000 represents the length in millimeters. So the length is 30,000 millimeters. So that didn't involve any calculus at all. This next one says L prime of 500 equals 0.2. So it's still 500 degrees because the inputs to L and the inputs to L prime are the same. But what is this 0.2? So it's saying we're over here, the temperature is 500, L is 30,000, and here we are, we've got that 1 point on the graph, and this 0.2 is telling us about the what of the graph? That's telling us the slope. So all I'm going to do is draw one little tangent line there because I don't know anything else. I don't know if the curve is concave up or concave down or linear, but I know that the slope here is 0.2. But the key to interpreting this question, to answering this question, is to get the units right. 0.2 what? So if you think back to that example we did the first day, where we also interpreted a slope of a linear function, units were crucial there. So this is 0.2. It's a slope, so it's a ratio of y values to x values. So this is 0.2 millimeters per degree. And when we answer this, we want to make it really clear that we understand that this is the instantaneous rate of change. So we're not talking about on an interval. We're saying exactly at 500. So at a temperature of 500, what is happening? Of 500 degrees, what is happening to the length of the bar? The length of the bar, well, we've got a positive answer. That means that the length is increasing. So the length of the bar is increasing at a rate of what we just figured out, 0.2 millimeters per degree. And if you go back and watch the tape about linear functions, we gave a preview of this back then. You'll notice that what words didn't we use at all here? We didn't use any word like each or every or for all, because we don't know that for every increase of 1 degree, the length will increase by 0.2 millimeters, because we don't know that this graph is linear. Back when we were doing a linear function, we were allowed to say that, because whatever the slope of a linear function is at one point, it's the same everywhere. So there you really can say for each one increase of whatever in x, you get some increase of whatever in y. We can't say that here. All we can say is at this particular temperature of 500, the length is increasing at that moment at a rate of 0.2 millimeters per degree. So please, on an exam, do not cost yourself points unnecessarily by saying something like that for every increase of 1 degree, we gain 0.2 millimeters. Because then it sounds like you think the function is linear, and you're missing the whole idea about it being an instantaneous rate of change. Finally, using parts A and part B, can we estimate L of 500? Now, it just says estimate. We're not going to be able to get it exact, but here we are at 500, and when the temperature is 500, the length is 30,000, and the slope is 0.2. So if you go over 1 degree, your estimate, and again, we can't be sure, your estimate is that the length will go up by 0.2 millimeters. So I think we could probably all answer this question without actually writing out any formula, although we are going to write out a formula in a minute. So if we go over by 0.2, we guess we go up if we go over by 1, we guess we go up by 0.2. If we're going to go over from 500 to 510, meaning we're going to go 10 units in the horizontal direction, how many units up would you estimate you're going to go? I think you would all agree that you estimate you're going to go up 2 units, meaning you started at 30,000, you ended at 30,002. And this is just an estimate. We're just doing the best we can of saying if it did stay at the same rate, what would happen? So let's try to write out as a formula how you got that answer of 30,002. I think you started with 30,000, which was what? That was L of 500. And then somehow you decided you were going to add 2 millimeters as your estimated gain in the length. And I think you got that by taking 0.2 times 10. This ended up being in millimeters, right? But what was the 0.2 in the language of math? That was our L prime of 500. And where did the 10 come from? That came from you started at a temperature of 500, you moved over to a temperature of 510. So we took 510 minus 500. And on an exam, you don't have to write out all these details. If you can just do in your head, by understanding the situation, say, okay, I knew that I started at a length of 30,000 millimeters, and I'm going to estimate that when I go over 1 degree, I'll go up 0.2 millimeters. So if I go over 10 degrees, I should go up 2 millimeters, and therefore add 2 millimeters to 30,000 and end up with 30,002. That's great. That shows you really understand the problem. Some people feel more comfortable if they have a formula they can rely on. That's also great. So that's why we're showing it to you both ways here. Let's try one more to make sure we get the idea. So now we've got a car that gets G of V miles per gallon. Sorry to all of you watching from outside of the United States. When driven at V miles per hour. So we want to interpret what these things mean. G of 65 equals 40. Again, this is no calculus here. This is going back to the very first day. What you need to do is get the units right. Is this 65 miles per hour or is this 65 miles per gallon? Well, V is the input and V is miles per hour. So at a speed of 65 miles per hour, I'm going to abbreviate that at miles per hour. What happens? The car gets 40 miles per gallon. Now we've got one with a derivative in it. G prime of 65 is negative 0.3. So here we are, just like we were there before. We're driving at 65 miles an hour. At that state, we get 40 miles per gallon. And all we know is 1 point on the graph, and we know the slope. Except this time, the slope is negative. So the slope is negative 0.3. And that probably agrees with what you've learned, which is when you're driving a car pretty fast already, like 65 miles per hour, if you speed up, your gas mileage actually gets worse, right? So it actually takes you, although it takes you less time to get to your destination, you burn more gasoline, you're less efficient in getting to your destination. And again, the key in figuring out, really understanding what this is to get our units. But just as in the previous problem, this is a slope, so it's the units on the vertical axis over on the horizontal axis. So it's miles per gallon per mile per hour. And people like to do this problem in 2 different ways, I've discovered over the years. Some people, such as me, understand it best if we just leave this in these units, miles per gallon per miles per hour. But I know some of you out there are saying this is just screaming out to have some simplification done, right? Miles per gallon, miles per hour, the miles will cancel, and you'll end up with hours per gallon. And if you want to think about this in terms of hours per gallon, that's a great way to think about it. But let's try to write it out one way or the other here. So we're saying that at a speed of 65 miles per gallon, miles per hour, what is happening? The car's gas mileage and what is the gas mileage doing? Is the gas mileage increasing or decreasing? We know that the gas mileage is decreasing because we have a negative slope. So the gas mileage is decreasing at a rate of, and again, you'll notice that we're really emphasizing that we understand that this is an instantaneous rate of change. There's no each, there's no every, there's no all. All we know is what's happening right at time 65 miles per hour. Decreasing at a rate of 0.3 miles per gallon per mile per hour. And again, if you want to think about that instead as decreasing at a rate of 0.3 hours per gallon, that's fine. And that makes sense, right? As you drive faster, you get fewer hours of driving pleasure per gallon. If you cancel the miles and you get 0.3 hours per gallon, driving faster, you don't get as many hours to drive per gallon of gas you spend. And finally, let's estimate G of 60. So just a reasonable expectation. Should we expect G of 60 to be more than 40 or less than 40? I hope you agree it should be less than 40 because this is this should be more than 40 because although this function is decreasing, we're going to the left, right? So we're going to go back to 60. So our estimate would be that if we go from 65 back 1 unit, we should go up 0.3 units. So if we go back 5 units, we should go back 5 times 0.3 or up 1.5 units. So if we're getting 40 miles per gallon when we're driving at 65 miles an hour, if we go back 5, we estimate we'll go up 1.5 to 41.5. So that's what we expect our final answer to be. And again, remember, these are just estimates. We're going to say if the slope stayed the same for those 5 units here. We can't be sure. So if we write this out as a formula like we did over there, we're looking for G of 60. That's approximately what we started with, which was G of 65 plus G prime of 65. So let's see how this all works out at the end. We said it's going to end up at 41.5 because we were getting 40 miles per gallon when we were going 65 miles an hour. But the rate of change was negative 0.3. That's what the G prime of 65 was. So how did this become a bigger number even if we had a negative there? That must have been because we had a negative here, right? We went 5 units backwards. So we went from 60 minus 65. And this is 41.5 miles per gallon. So the important thing for both of these examples is that when you're interpreting the rate of change, you want to be clear that you're indicating that you know that it's an instantaneous rate of change, not that you're thinking that the function is a linear function. And we have a check your understanding to see if you have grasped that idea.